yeah, I want to talk about a Lagrangian intersection result and then and some consequences for symplectic embeddings. So this is joint work with Ely Kerman. All right, so can you see the top of that? Anyway, okay, so just fixing. Oh, is this coming through? So I'm working in.
So sorry,
just in our...
now we don't see the top, actually, unfortunately. There's something there, we don't see the top line.
Maybe my PDF is too big. Okay, maybe I have to... Okay, I could just scroll. How about that? It's better. Worse.
Yes, if you scroll, we do so. No, we do see the top now. Yes. Yeah.
But not the bottom. I can scroll anyhow.
Yeah, yeah.
Not the bottom. Okay, all right. So this is just notation anyway. So I'm just working in. We don't have much to say in high dimensions, so just working in R4, the standard symplectic vector space. Usually identify that with C2, and then then we'll be talking a lot about product Lagrangian tori. So these are just products of circles in the Z plane and the W plane. And also people talk about ellipsoids and polydiscs. So they're defined there. So in this notation, a ball of capacity A is EAA, and a cylinder of capacity A is PA infinity. All right. Then, so these are all examples of what I'm calling toric domains. So just pullbacks of subsets of R2 by the moment map. All right. Okay. So that's the notation. Then, okay. So the motivating question for us: if you're given two omega-1, omega-2, just subsets of R2, they correspond to toric domains. Does there exist? Right. So I'm saying, does there exist a Hamiltonian diffeomorphism taking one domain into the other? Right. So this is a version of the symplectic embedding problem. Well, so first of all, I'm just restricting to toric domains, so there's a restriction there. But also we're only considering symplectic embeddings that extend to global Hamiltonian diffeomorphisms. And so that's a restriction. So in particular, you can't map an annulus into a cylinder with this definition. Okay. Anyway, so we'd like to solve that problem, and then I'm going to try to investigate it using what we call the Hamiltonian shape invariant, which is this. So all it's doing is just recording pairs RS such that the corresponding product Lagrangian embeds into X by a global Hamiltonian diffeomorphism. Right. So here, I might as well restrict to R less than S because LRS is Hamiltonian diffeomorphic to LSR. So there's some symmetry here. So we can assume the shape sits inside R less than S. So that's our definition. So this is from a paper with Jun Zhang. There's Ely Ashberg had a more general definition, I think in 91, around there. So he was just keeping track of area classes of Lagrangians inside general exact symplectic manifolds. So for our problem, it's helpful to keep track of Hamiltonian isotopy classes. So there's a little bit more information there. Okay, so that's it. That's the shape invariant. Then maybe even before Ely Ashberg, really sort of studying spaces of Lagrangians like this goes back to maybe, well, Benchy-Sakharov theorem can be sort of on these lines as well. Okay, anyway, all right, so that's the shape. Then, all right, so some properties of the shape. All right, well, so first of all, more or less, the moment image sits inside the shape, except we have to do this little correction because I'm writing the factors in order. So it's, all right, so this sort of symmetrized version of the moment image is a subset of the shape. Then the other two properties, it scales nicely. So if you scale omega, the shape scales. And it's monotonic under Hamiltonian embeddings, remember, right? So when I write this arrow, I mean a Hamiltonian diffeomorphism taking one domain into the other. So, all right, so it's a monotonic under embeddings. It's a subset of R2, though, are the one octant in R2. So we say it's you can say it's like a set-valued symplectic capacity. Right, so it takes values in subsets, but otherwise it looks a bit like a symplectic capacity. All right, so it's okay. All right, so we have some capacity. Then it's possible to compute it sometimes. So we did it for balls, cylinders, polydiscs, and to work with Opstein, and also certain ellipsoids. I worked out with Junzhang again, and then and these are the results here. Okay, I'll do two layers. Right. So first of all, right. Well, so what I'm drawing here, the black's outlining the moment image, and then the green is the corresponding shape. So so there it is. So the cylinder, you basically just get back the cylinder itself when you take the shape, apart from this restriction that it has to sit above the diagonal. Ball, the same thing. You get the shape, gives you the ball back, except now there's this strip going up the y-axis. So we'll talk about that. So there's this strip of radius a/3 going up the y-axis. Then there's a similar situation for polydiscs and ellipsoids. Right. So polydisc again, you get the moment image with this strip. The strip now has width a/2, and the same for these ellipsoids. Right. So those are various sort of first calculations of this shape. Okay. And then, well, it's just the slide where those strips are coming from. It turns out there is, if you have any R and S, R less than S here, there is a Hamiltonian diffeomorphism taking the Lagrangian torus into the toric domain for this this quadrilateral here. So that means every time you see this quadrilateral, this trapezium, every time this trapezium sits inside the moment image, you're guaranteed to get a strip of the corresponding width. And so that's so somehow these strips are sort of inevitable because of that. Anyway, so that's where they're coming from, and this is a very explicit symplectic embedding. All right, so okay, then there's some discussion slide here. So based on based on all this, the shape it's not like it's some sort of complete obstruction to all symplectic embeddings. Really for two reasons already. First of all, because of the strips. So for instance, this sees nothing about, for example, if you want to embed a thin ellipsoid into a ball, the shape that I've got here sees nothing, right? Because the thin ellipsoid would sit purely in the strip part of the shape of the ball. So there's no obstructions to embedding thin domains into sort of rounder domains. So in particular, all that picture of ellipsoids into balls is a very beautiful story, worked out, I suppose, completely by McDuff and Schlenk. So that whole, there's a Fibonacci sequence there, and that's all invisible to the shape. So that's a shame. And also, we lose a bit of information because we only see omega plus and not the actual moment image. So, so for example, so looking at those pictures, you see that the shape of a ball is contained in the shape of a cylinder if and only if C is less than 2R. So, we're not, so based on this, I'm not even reproducing the non-squeezing theorem. It's out by a factor of 2. Okay, so anyway. Well, if you did want to prove, it's like an aside of an aside here, if you did want to prove the non-squeezing result, that it is possible to actually extract more information from the space of Lagrangians. So the idea is that if you had one of these Hamiltonian embeddings, you don't just get, well, right. I mean, you get embeddings of each Lagrangian inside the moment image, but actually those embeddings vary smoothly with the point in the moment image. So actually, I get exactly the hypotheses of these of this proposition here. So if you assume not just that there's an embedding of each individual Lagrangian, but if you assume that there's a smooth embedding of all Lagrangians in the moment image for a ball into a cylinder, then a consequence of that is the non-squeezing result. And so looking at the shape, we are kind of throwing out information about the topology. So we're keeping track of which Lagrangians are in there, but we're kind of throwing out the topology, and that's losing information. All right, so there's that. So this, so the proof of this is to do with controlling flux of Lagrangian isotopies. So it's so once I can embed all Lagrangians inside the moment image, I can read off a lot of Lagrangian isotopies from that with a determined flux, right? And there's various other works on that. Okay, anyway, so that's what the shape's doing. And so I guess now it turns out, even if you had a smooth family of Lagrangian embeddings for all Lagrangians in the moment image, that's still not enough to get you a symplectic embedding. But I mean, it works in the case of a ball, but in general not. But what it gives you is what's called a stabilized embedding. So that's more or less what this is saying. Right, so that's another explicit construction here. So you have a smooth family of, right, so now a smooth family of Hamiltonian diffeomorphisms for each Lagrangian inside the moment image. And then, right, then based on that, you can generate what we call a stabilized embedding. So from the original toric domain times C to the new one times C. Right, so that's right. So okay, right. So keeping track of families of Lagrangians gives you this. But we know now that stabilized embeddings, it's a weaker condition than an actual symplectic embedding. And there's some explicit constructions that show that sometimes the converse is true. So the stabilized embedding implies you get the family of Lagrangian embeddings. So I suppose it's possible to conjecture these are the same thing. We don't have a direct proof, though. That's just by two calculations on both sides and checking they give the same answer. Right. Okay, so that's right. I think that's it. So that's right. So that's the shape and what we can kind of general facts about it. So I don't know, any comments on that? Questions there? Okay, clear? That's fine. All right. Okay, so then this is what we want to prove. Right, so this is this Lagrangian intersection result. Right, so there's some restrictions. So I'm assuming that R is bigger than a half, S is bigger than 1. Then, okay, right, so suppose I have a Hamiltonian diffeomorphism of C2, which takes the product Lagrangian torus and maps it back into the cylinder. Then the claim is that that's the image of the torus has to intersect K. Right? So K is a family, a one-parameter family of Lagrangian tori, right? So just these LRT. So I suppose it's a codimension 1 submanifold with boundary LRS. All right, I'll talk about these various hypotheses in a second. I've got a picture about this. Okay, so that's the theorem. There's also a variation. If you happen to know that the Hamiltonian diffeomorphism takes the Lagrangian torus back into a polydisk, so not just anywhere in the cylinder, into a particular polydisk, then in fact it would have to intersect your original Lagrangian. Okay, so that's the similar proof of that. So the novelty, I guess, the novelty in the second one is I'm not assuming that phi is compactly supported in the polydisk. So in particular, so this phi LRS, it's Hamiltonian isotopic to the to the Lagrangian in C2, but it might not be Hamiltonian isotopic to the product Lagrangian in the polydisk. So it seems hard to get at this using Floer theory methods. Okay, anyway, so those are the main results here. All right, and then this is a picture. So this is what would happen if you took the moment's projection of everything. All right, well, okay, right. So the cylinder, we know the cylinder is just this vertical strip. The Lagrangian LRS, that projects down just to the point, right? The point in the middle here. K is the pre-image of the vertical line going up from RS, and then right, and then I don't know what the moment image of the image of the product torus is, but the claim is that at some point it has to intersect K. So right, so the way I've got it drawn here, so that the moment image would have to intersect that vertical line. So that's the claim. Okay. Right. Okay. All right. Well, that's right. So we'll have to try and prove that, but there's some discussion about this. So it's so I'm trying to claim. Go back a second here. Right. So I'm trying to claim that a Lagrangian intersects this codimension 1 submanifold. So it's kind of a natural question if you could replace that submanifold by something smaller. Sorry, I was going to talk about the hypotheses here. So all of these hypotheses, I claim what we need, right? So the first one was that R has to be bigger than a half. Otherwise, this is false, right? So if R is less than a half, then you can just apply a Hamiltonian depending on the Z coordinate and sort of shift it horizontally and displace the Lagrangian from this K. And then there's this condition that S has to be bigger than 1. So the reason for that is, it would be nice to somehow replace this with something, but S has to be bigger than 1. So that's again this fact that LRS is Hamiltonian isotopic to LSR. Not necessarily inside the cylinder, but globally Hamiltonian isotopic to LSR. So in principle, phi LRS could be LSR, and that is disjoint from the K. So right, so to exclude that kind of thing, I need to assume that S is bigger than 1. So that's why that condition's there. And then also we do need something for K, right? It's not true that the Lagrangian has to intersect itself because I have infinite amount of space in the W direction. So we need something there for the K. All right, but nevertheless, you could ask if K could be replaced by something smaller, like maybe some family of Lagrangians in there. Right, so I want to talk a little bit about that. Right, so it's so all right, so I'm going to try and make that question a bit more precise. Right, so okay, so we fix a number B. All right, so I'm going to assume it's right K plus 1 times S minus G. Okay, let's do that. All right, where G is between 0 and S. So then, right, so inside the disk of area B, I can get K disjoint circles bounding area S. Okay, right, because B has area bigger than KS. And then what G is doing, if you tried to you couldn't put a K plus first one in there, and if you tried, it would have to overlap the previous ones in some region of area G. Okay, so G is some sort of obstruction here. Okay, right. So we've got these circles in the disk in the W plane. So now I want to take a product, just take a product with the circles of area R in the Z plane, and then I get a family of Lagrangian. I get a family of Lagrangian tori. Right? Or you could say it's a Lagrangian packing of the polydisk. All right. So, for example, if I just took the first circle just to be the round circle of area S, then L1 here is just going to be our product torus, LRS. All of the other LIs, well, all of the other lambda i's would sit outside of right. Well, they're outside of lambda 1, and that means the corresponding LIs are going to be in the K. All right, so it's so we have a Lagrangian packing consisting of tori sitting inside K, and you could ask if phi LRS has to intersect one of these lambda i's. All right, so that would be a question. And there's a positive results in that direction due to Polterovich and Shalukin. Right, so they said if G is big enough, so somehow, so I'm kind of imagining here, the larger that overlap area is, the harder it's going to be to get an extra Lagrangian in the polydisk. All right, so okay, right. So if G is big enough versus R, right, okay, then there's this other hypothesis. So they're using Floer theory eventually. So it's the other hypothesis. Now we're assuming that phi is a Hamiltonian diffeomorphism of the polydisk. Then indeed, phi of LRS must have to intersect one of those LIs. So it's so in other words, right, so phi, right, so LRS can't be displaced from this Lagrangian packing. So there's that, which maybe suggests, maybe K can be replaced by something smaller. However, it turns out, so there's a nice paper of Hicks and Mack doing constructions on these lines. And if we follow their methods, we get the following. So unfortunately, the bounds don't quite match here. It's a bit of a shame about this 6, but anyway, it's the best we can do at the minute. All right, so okay, so conversely, so suppose the overlap area is small compared to R, then not only can I displace the product Lagrangian from all of the LIs, but I can even displace the whole corresponding polydisk. So so this sort of forced Lagrangian intersection fails completely when the overlap area is small enough. So it's so in particular, applying this to our situation. So I'm working in the cylinder. So there's in the W plane, there's, well, it's the whole plane. So what we want to do is, so I'm going to take the polydisks. I'm going to let B run to infinity. Then the K would run to infinity. And then what you end up with is this. If you take any family of Lagrangian circles in the W plane, all bounding area S, then doesn't matter what you do, you can find a Hamiltonian diffeomorphism of the cylinder, which displaces the product torus from all of the corresponding LIs. Okay, so that's the so in other words, so this is it's a long excursion, but the this is all really to say that it's hard to see how to replace K by something smaller, at least in this scenario. So all right, so that's right, okay, so that's what we have. So then, all right, so then back to the shape. So this is supposed to say things about the shape. So there's the corollary of the first result and the second one. So right, so first example, right. So I'm assuming my toric domain is the area under a graph. All right, so it's right. So f is a function. I need to, okay, we'll come back to that. I need to assume that f takes values bigger than 1. Anyway, it's a function on the interval. Omega is the area under the graph. Then it turns out the shape is exactly, well, this symmetrized moment image together with a strip of width 1/2. Okay. And then the second one, you can drop the graph condition if you assume that the moment image is between the square and the rectangle. then we get the same result, right? So then the so the shape is exactly the moment image together with this strip of width a half. Right, so that's so we get a lot of calculations of the shape. Okay, which I'm going to draw. So these are the examples. Right. So what's going on here? So now, so putting all this together, we get a map from subsets of the plane to subsets of the plane. So what it does, so you take a subset of the plane, that corresponds to a toric domain, then you take its shape, and that gives you back another subset of the plane. So I get a map from subsets of the plane to subsets of the plane. The first result is saying, okay, if you start with the area under a graph, and the graph looks a bit like that, then you get exactly the same region back, but together with a strip going up the y-axis of width 1/2. And this is supposed to be a direct corollary of our result. So if you wanted to prove this, well, first of all, we've got to spot that everything in the green area here on the right is actually in the shape. So the stuff in the moment image for sure is in there because it's you can just take the inclusion map on the Lagrangian. But then the domain I start with contains the square. So in particular, there's one of those trapeziums in there. Turns out the parameter on the trapezium is a half. So that means, so because that trapezium's sitting in there, that implies that I get the strip of width 1/2. So the shape certainly isn't any smaller than this. But then, then you say, maybe there's more stuff inside the shape. So maybe, you can see this cursor here, but anyways, maybe suppose you get some points like just to the left of that, that hump. And so suppose we get an extra point. What would that mean? That would mean that the corresponding Lagrangian torus could be mapped inside the toric domain. But since in that case, though, the image of the torus would be, well, it would be displaced from itself, but in fact, it would be displaced from all of K. And that would contradict our result. So that's, so our result says, so we already know the shape can't be any smaller. Our result says you can't get anything else in there. So it's the first example. Then, if I happen to have more control on the original domain, so for example, if it's bounded between 1 and 2, then in fact you can drop so you can drop the graph assumption in this case, right? So it's so now the thing doesn't have to be a graph, doesn't have to be simply connected, whatever you want. So you're going to get the same domain back plus this strip. Okay, so that's what we have. So it's so I suppose the takeaway for us is that this shape sees nothing about somehow thin domains into round domains, but away from that, you get a pretty good list of obstructions. And it's I suppose you can get sharp results out of this in a lot of cases. All right, so that's that's what we have. So I don't know if that makes sense. Okay with that. So it's right. So we can compute the shape in a lot of cases, and and they rely on that result. So that's it, I think. So now, so all I've got to do is try and convince you this might be true, I suppose. Okay, so now, so this is now the proof. So this, so so I'm going to go with this. So the thing is here, we're dealing with non-monotone Lagrangian tori. So we did, so me and Ely, we had a similar argument for tori in the monotone case. So now but now, we have to work to calculate the shape. We need to work with non-monotone tori. So All right, so there's a bit of notation, but I also have some pictures, so it's so bad. Right, okay, so all right, so how it goes, right? So we'll argue by contradiction. So I'm going to call this like bold L maybe. So that's the image of my Lagrangian tori under some global Hamiltonian diffeomorphism of C2, and by assumption that lies inside the cylinder. But it's disjoint from the K, right, from the pre-image of that vertical line. So at least when B is large, right, everything's compact, we might as well assume it's sitting inside some large polydisk. And then, right, there's like a little technical thing here. We know that R it's at least a half. So I'm in a sense, I'm kind of reducing to the case when R is exactly a half. Or in other words, we're putting the polydisk inside a potentially larger polydisk, just because it makes area calculations a bit easier. You don't have to worry so much about homology classes to compute areas when we do this. So, okay, so we put the Lagrangians inside some polydisk, and then the usual thing, you can compactify the polydisk to get a copy of S2 times S2 with those areas 2R and B. All right, and then in the S2 times S2, I'm labeling the axes, just what they are here, right? So S0, S infinity, T0, T infinity. Right. And then there's a completely like not obvious thing, but so for sure, so because I'm adding them on in the compactification, so for sure the Lagrangians are disjoint from the S infinity and the T infinity. LRS is the product torus, so I just know that it's disjoint from S0 and T0. But now I'm claiming this kind of a stretching argument. We can also assume that the bold L, that's the image, is also disjoint from S0 and T0. So that's it's not obvious, but somehow I want to assume that's true. Okay, then given that, then we can draw this picture. So this is the scenario arguing by contradiction, right? So now I'm in a copy of S2 times S2. I've got the axes labeled. K, I'll just call K this thing here now. Right. So now, right. So right, yeah. So the assumption is I have two Lagrangian tori, LRS and this bold L, sitting inside S2 times S2 minus the axes. And the goal is to show that they have to intersect. So you can almost kind of imagine how this is going to go. So it's so right. So once I'm assuming they're disjoint from the axes. Once we throw the axes out, what's left we can identify with a subset of the cotangent bundle of T2. Up to translation, I might as well assume LRS is the zero section. So the problem is to show that the bold L has to intersect the zero section. And for that, there's a theorem of Gromov. So it would be enough to know that it's an exact Lagrangian torus. But to go about checking that, we're sort of doing it in two stages. The first business is we'd like bold L to represent the non-trivial homology class. And then once we know it's in the right class, then we want to check some areas and check that it has to be exact. So that's kind of the scheme. So it's two steps. We've got to worry about which homology class in the cotangent bundle of the torus bold L is representing, and then I want to check some try and calculate some area classes. All right. Okay. So it's all right then. So to get a handle on that, we're going to have to use holomorphic curves. All right. So it's okay. So now, all right. So okay. So it's again this story goes back to well, to Gromov. Actually, this idea of getting estimates on the shape based on Gromov's results on exact Lagrangians, that argument was already used by Sakharov in a certain case. Although he somehow the Benchy-Sakharov theorem, you kind of automatically know that the Lagrangians are homologically non-trivial. So they get that for free. But anyway. Okay, anyway, right. So we fix almost complex structure, can assume it's standard near the axes. There's some monotonicity estimates going on. So in fact, I want to assume always that J is standard on this like added strip on the right here. So that's somehow we're using that. Okay, right then. So there's a foliation by holomorphic spheres in the class of it's the class S2 times a point. Foliate by holomorphic spheres there. By positivity of intersection, each sphere intersects S infinity in a single point. So projecting on the leaves, we get this projection map from the S2 times S2 to the S infinity. And then my T's are the fibers over T0 and T infinity. Okay, so got that picture. So we want to so we want to refine it a little bit to take account of the Lagrangians. All right, so I don't just want to work with smooth, almost complex structures. I want to work with almost complex structures which are stretched along the two Lagrangians. So, so in other words, if we're thinking of almost complex structures on X, they would be singular on the union of the Lagrangians. Alternatively, you can think of, to same up to diffeomorphism, you can think of stretching the neck along tubular neighborhoods of the Lagrangians, and these are the complex structures on the completion of the complement of the Lagrangian. Anyway, okay, so this is right. So now this is a manifold with cylindrical ends. Now we have a finite energy foliation. So it's just, right, so what does this mean? So still a foliation. The generic leaves are still spheres, but now there's one parameter families of what we call broken curves. So a broken curve is going to consist of finite energy planes with asymptotes. So it's, well, right, in this picture, they're going to be asymptotic to geodesics on one or other of the tori. Right, so this turns out you still get a projection map as before. And so in principle, the projection map is just defined on the complement of the Lagrangians, but it extends over the Lagrangians. And then I'm defining gamma and lambda to be the projections of the two tori. These are circles, but in general, they might not be embedded. So, right, so there's a lot of stuff going on here, and we're relying a lot on the paper of Goodman, Ivry, and Dimitroglu-Rizal. So it's right. I'm trying to draw. Okay, so I've got a picture. So I'm claiming we get something like this. So this is X. So this is S2 times S2, same as before. I have the two Lagrangians in there. Then these the red, whatever they are, right? Those red sketches are supposed to represent the leaves of the foliation. So generic ones are closed spheres intersecting S infinity in a single point. And then I've drawn one possible scenario here, right? So I'm drawing a scenario where the broken curves are exactly pairs of planes matching, right? So finite energy planes matching along a geodesic on the Lagrangians. So this is it's possible there's more complicated pictures. So I'm drawing one possible scenario here. In particular, there's no broken curves with asymptotes on both bold L and LRS. So that's the way I'm drawing it. So if we assume that's true, then when you do the projection to S infinity, that means the projection of LRS and the projection of gamma are going to be disjoint, right? Because there's no leaves that go through both LRS and bold L. So the projections of the two tori in this picture are going to divide S infinity into three regions, A, B, C. Right. Okay. So this is a special case. It's one example of what might happen. Yeah, I'm also right. So it's actually what I'm also drawing here. So there's by some index counts, there's one parameter families of broken curves. So I'm assuming those one parameter families are one parameter families of finite energy planes. So in other words, the Lagrangian tori are going to bound two solid tori, and each of those solid tori is foliated by holomorphic planes. All right. Okay. So that's right. Right. So I'm labeling those families P0, P infinity, Q0, Q infinity. Okay. Right. But the lemma is this picture is exactly what happens. So it's not clear this is what's going to happen in general, but I claim in our situation this is exactly what we get. Right. So the broken curves are exactly pairs of planes. Each of the planes has area R. The two circles are point 2 here is actually a consequence of 1. So because there's no broken leaves connecting the two Lagrangians, the circles are a disjoint. And then important for us is that this picture at the bottom is, I'm drawing the circles the right way. Okay, so in particular, gamma separates lambda from infinity. So I wonder, that's kind of important for us. Right, so I don't know how much to get into this, but so this is a bunch of so part 1 is based on sort of area estimates. We're really so we can control the possible degenerations because we're stretching holomorphic curves of area 2R. So there's not too much energy to play with. So if I just go back a little bit here, so if maybe I stretch the neck and get one of these broken curves, one half is going to have to miss S infinity, and then because of the Lagrangians I'm looking at, this half would have to have area at least R. The other half would have to go through infinity. Since it goes through infinity, it has to go through that added kind of inflated tubular neighborhood of S infinity. That means the other end has to have area of at least 2R minus 1. And then putting that together, that means the first curve has to have at least R, but less than 1. And then the only option for a Maslov 2 class is R, because of the assumption on S. So anyway, so they break this way basically because there's not enough area to do anything else. And then the interesting thing is why does gamma separate lambda from infinity? And this is exactly where we use the assumption about K. So because I have this assumption about K, I can do some kind of continuation argument and trace LRS. I've got it written here, right? I can trace LRS and find a Lagrangian isotopy, trace it through LRTs until T gets very close to B. In other words, until the Lagrangian just becomes a small Lagrangian about infinity. And there, for the LRT, it's clear that the corresponding circle is going to loop around infinity. But then we can do a continuation argument exactly because the bold L is disjoint from the K. So that's where this assumption is. The assumption about the K is coming in. All right. Okay, so that's right. So we got this. That's the holomorphic curve setup. All right. So now, so I guess now I'm pushing on. Remember the goal here. I have to show these Lagrangians are exact. So the next job is to start computing areas, and then this is the result here. So it's right. Right. So remember what those. So remember the S infinity is divided into 3 regions, right? A, B, C. A was a disk. The boundary of that disk is on lambda, which is the projection of bold L. Then, right, it's easy to see that, in fact, there's lots of ways to do it, that disk lifts to a Maslov 2 section with boundary on L. So there's lots of ways to do this. You could lift it to different relative homology classes, but it doesn't matter what you do, it's always going to have area S. So that's so again, this is maybe I'll skip this one. So again, this is because we don't have that much area to play with. There's only so many possibilities. So it's right. Okay. And S is the same as the S is the same as the area of the Maslov 2 disks with boundary on the product Lagrangian. So this is the kind of thing we want to be true to show that one is exact relative to the other one. So both those Maslov two sections have area S. Right. Okay. Well, right. So it's not completely trivial. Right? So it's so you sort of check off the the area possibilities. That gets you down to S or 2R minus S. 2R minus S we have to exclude by proving that they can represent this by a holomorphic curve. And then we can use the monotonicity. So, okay, so that's the area estimates. All right, so now, okay, so this is referring back. So back to that picture then, right? So now the claim is that the picture I drew about these foliations is correct. So there's the two families of planes asymptotic to LRS. There's the two families asymptotic to bold L. Okay, so I can assume, because LRS is the product torus, that P infinity intersects S infinity, P0 intersects S0. I'm just going to define Q infinity to be the family of planes intersecting S infinity. But then there's two ways this could go. So it's possible that the planes in Q0 also intersect S0. But suppose they don't, right? So suppose the planes in Q0 intersect S0, which is kind of the way I had it drawn. Right? So one family intersects one axis, the other family intersects the other axis. If that is true, then indeed LRS and L and bold L are both homologically non-trivial in the complement of the axes. And in that case, we can go on and get a contradiction. All right, so it's right, so kind of going through this, right? So then the complement of the axes is can identify that with a subset of the cotangent bundle of the torus. The product Lagrangian, we can translate, make that the zero section. And then by these various area estimates, right, the Q's have the same area as the P's. The sort of the Maslov two sections have the same area. That's enough to deduce that bold L is an exact Lagrangian torus, and then that's a contradiction to Gromov's theorem, because exact Lagrangian tori have to intersect the zero section. All right, so that's right. So the proof's nice in that case, but this is assuming that the Lagrangian is right. The bold L is homologically non-trivial, and maybe that's just not the case. So in fact it's all right. There's work of Chilibach and Schwingenheuer on this, and sometimes if you assume it's homologically non-trivial, we could also use this paper of Goodman, Ivry, Dimitroglu, Rizal. That's almost enough to that does imply that the bold L is not a Lagrangian knot. So it's right. It's Hamiltonian isotopic to a section, and that just might not be the case. So okay, so right, so this is the main concern then. So we need to well, I suppose I'm arguing by contradiction. So I might as well assume now that L, when you do all this, that it comes out homologically trivial, which is the same thing as saying that those planes Q0 are disjoint from the axes. So then the argument's going to fail. But the strategy is to use a new set of axes. All right, so I want to substitute the S0 and the S infinity with maybe some alternative axes, which are going to force bold L to be homologically non-trivial with respect to those axes. Right, but to do that, I'm going to want some holomorphic curve to intersect the family Q0, and maybe that is impossible with holomorphic curves just in the original class we were looking at, right? In the class of S0. So in order to have enough flexibility to get a holomorphic curve where we want it to be, we need to look at curves of higher degree. Right? So in this notation, so curves in class D1. Right? So these things have much higher index, and maybe there's more flexibility to get them intersecting these planes where we want. Okay, so now I want to play with these high degree curves. You can stretch the neck and disjoin them from the Lagrangians, but it turns out I want to control the intersections between the high degree curves and the pairs of planes. And it turns out the easiest way to do that is, first of all, to stretch the neck and force them to kind of maximally intersect the Lagrangians first of all, and then push them off in a controlled way. All right, so this is what I'm doing then. So I'm So I'm looking at curves of high degree here. We can assume they go through 2D plus 1 points, and I'm putting all of those points on the 2 Lagrangians. Then we do a neck stretching, and then and then take the limits, and I'm going to get a holomorphic building. All right, so then the question is, what does this holomorphic building look like? And there's so there's a bit of analysis here. So how these things go. But because there's a whole bunch of constraint points on the Lagrangian, these holomorphic curves are going to break. They're going to break along the Lagrangian. But we can kind of control the breaking a little bit. So because these holomorphic curves, the homology class I've chosen, they're all still sections of this foliation. So the limiting buildings, the components are either still sections or they cover fibers. So there's sort of two possible scenarios. The P's 74. This circle on the bottom is supposed to be gamma. I think it's gamma, right? So this is a picture near P inverse of gamma. So P inverse of gamma is the Lagrangian torus. Right, so you sort of do some positivity of intersection arguments. There's kind of two scenarios. So either there's one curve nearby that projects injectively. Right? So the blue curve, I'm calling that type 2. Or there's two curves nearby that project injectively. So one of two scenarios happen. Right, and we claim it's always the second one. It's always going to be the second one that happens. Both near P inverse of gamma and P inverse of lambda. Right. So, and again, this is another sort of area calculation. So it's so we just somehow check off the possibilities. So the idea is, well, okay, I'm ruling out one possibility here. So suppose we got type 2. I'll just go back up again here. Suppose we got type 2 near, okay, I've switched the one. Suppose I got type 2 near P inverse of lambda. So what does that mean? So type 2, that means I'm getting a bunch of planes covering leaves of the foliation. And in fact, all of those planes have to lie in the same family. So either they're all in Q0 or they're all in Q infinity. And suppose they're all in Q0, then the thing is these planes are taking a lot of area. So like order D of area, but they're not contributing any intersections with infinity. So then you kind of calculate, well, how much area does the rest of the building have? Well, not so much, because it's costing me a lot to produce all these planes. So the rest of the building has bounded area, but it still has to intersect infinity order D times. And then you can kind of argue that that's a contradiction to one of these monotonicity estimates if you run D off to infinity. So it's somehow a very indirect argument, this, but that's right. So that's why I can't exactly say how large D has to be, but anyway. So the claim is if you take D large enough, then the curves are going to break in this type 3 way. And okay, so if they break in type 3, that means as you approach each Lagrangian, you always have two different curves, two different components of the building, asymptotic to each Lagrangian. And then the picture, I'm changing orientation here for some reason. It's for the artwork. So putting all of this together, the claim is if you take a limit of these high degree curves, you get something like that. Right? So it's okay. So in other words, so this is supposed to be describing the type 3 breaking. All right. So So somehow I'm imagining the curve on the left is projecting to A, the curve, like the cylinder in the middle, is projecting to B, the cylinder, and then the curve on the right goes down to C. Then all these vertical looking disks are supposed to be covering leaves. So that's the so the claim is you get a building like that. And then there's a lemma that I can kind of push this off in a controlled way. All right. So a holomorphic building, like a whole bunch of holomorphic curves, just individually, I can just move each of them away from the Lagrangian. All right. So and when I do it, I want to push the leaves a little bit to the sides. So a little bit like how I've drawn it here. So we want to push all the constituent curves away from the Lagrangians and then just fill them in with a sphere with punctures. So we don't have to be too precise. All I care about is a symplectic curve, really, at least in the other Lagrangians. So we kind of push the building off, fill it in with a multi-punctured sphere, and then I get a high degree symplectic sphere in the complement of the Lagrangians, but I have some control on what it looks like. In particular, I can choose whether it intersects the Q family or the Q infinity family, and the P0 or the P infinity family. So these are the holomorphic spheres. This is going to be my substitute axis. Okay, almost done here. And then there's a big lemma about doing that. So there's okay. So there's two ways. So actually, I need two axes. So I've got to start with two holomorphic buildings, and they're just set up a little bit differently. So one has D constraints on the product Lagrangian, the other has D plus 1, and then vice versa for the bold L. So we have two holomorphic buildings, and then I deform them to get holomorphic spheres, kind of like was drawn in that picture. So, right, but we have control on this deformation. So I can assume exactly, well, one of the F or G intersects P0, the other one intersects P infinity, one intersects Q0, the other intersects Q infinity. But the trick is we can arrange this because I'm kind of pushing all the planes to the left or the right. I can assume that all the intersections between these holomorphic spheres occur on the two ends, right? So either on P inverse of A or this should be a C, by the way. So this is right. So what I'm claiming is, if you imagine drawing this whole picture again with some other curve, but where I push this one down, I push the other one up. Right. Okay. I'll do the same here. We can arrange it to somehow maximize intersections on the two ends. So these two curves, these two spheres now, they both have degree D, and I'm kind of arranging that all of the 2D intersections appear on the two sides. Right. Okay. So there's a bit of intersection counting there. Okay. And now I think now we're basically done. Right. So now, right. So the two spheres have self-intersection 2D. Right. But they intersect in 2D points. I really want them to be axes of an S2 times S2. So I want self-intersection 0, but that's easily fixed, right? So we just blow up the 2D intersection points. Well, this is going to get me in a blow up of S2 times S2. Then I want to blow down the I want to blow down the proper transform of the fibers through the intersection points, right? So I'm not touching the F hat and the G hat at the second blowdown. I'm just blowing myself back down to S2 times S2. Okay, so we blow up the intersection points, blow down the transform of the corresponding fibers. That gets us back to S2 times S2. But now I have two spheres, F hat and G hat, now have self-intersection 0, and now they're disjoint. And then there's general classification results about S2 times S2, going back, Gromov again, McDuff. So the result here we can identify with S2 times S2, but again, I can take the T's or the transforms of the T's back to the horizontal axes, but now the F hat and the G hat become the vertical axes. The area class changes, but we don't care. But now the point is that still the L, R, S, and the bold R are still going to be disjoint from the axes, basically because they were disjoint from S, F, and G by construction. But now they're both homologically non-trivial and relatively exact. Right? So they're homologically non-trivial exactly because now I have axes intersecting each of the families. And the relatively exact thing, that's related to pushing all the intersections off to the two sides. So the thing is, if you started this whole blow-up business, so when we do this blow-up, blow-down, I'm changing the areas of Maslov two disks, but I'm changing the Maslov two disks asymptotic to the different tori in the same way. So they somehow stay relatively exact. And that's to do with pushing all the intersections off to the two sides. And then we're done, right? So then I have two relatively exact Lagrangians. Maybe we need to use Goodman, Ivry, Dimitroglu, Rizal here. Maybe the product Lagrangian isn't the zero section now, but they have a classification result. There's a classification of Lagrangian tori. Using them, I can assume the product Lagrangian is the zero section. And then by Gromov, you have to have an intersection. And that's a contradiction. Okay. All right. So I'll leave it there. Thank you.
Yeah, thank you very much, Richard, for this very nice talk. I don't know if there are any questions. Please go ahead with questions.
Richard, when you did this theorem where you have this graph, so you have the cube in the my picture, and then over the x-axis, the graph. Can you add a graph over the y-axis, or is it hopeless? The upper
You mean
one,
this
right?
top one?
Exactly. Now on the left-hand side, add also a graph over the y-axis. Maybe a kind of smaller one.
Do you want to take like the union or something?
The union of such two bands, right? Is then
okay, so you want a little bit kind of coming out at the right.
Is
that the plan? Well, I mean, okay, it'd be very nice. This is all related to that assumption that I need S to be less than 1.
Yeah.
So the problem is I can take an LRS and map it to LSR. So somehow, yeah, it'd be very nice to understand that. I guess I don't really know the answer, but maybe it's false, like trivially, if you state it in that generality. But I think there should be some result there. So somehow this is holding us up a bit. Just having to cut off this shape is a little bit restrictive. Yeah, I mean, a lot of like nice toric domains kind of bend down to the axis, and I'm kind of like ruling those out.
Yeah.
So it would be nice to get. Yeah, so I guess I don't know. I think it's probably false as stated, but there should be some theorem there, which would then right, exactly, and that would really open this thing up. And then
Thank you.
Yeah. Maybe other questions?
Yeah, so in your initial intersection result, there was this question of replacing the set by smaller set.
right.
And it seems to me like a natural candidate would be taking union of Lagrangian tori, like LRS union, LR2S union, LR3S, for example.
Right. Yes. Yeah. So that's true. That would be a natural thing, but in that case, it's somehow even easier to displace. So somehow all this stuff. Well, okay. I think the Polterovich-Shalukin result fails in that case, but these propositions still hold. So kind of the displacement results still hold. So the thing about that case is the overlap area is basically 0. I can kind of get a k+1th torus in there, which barely overlaps. So in that case, it's, yeah, so you could do that, but in that case, it's still possible to displace from that thing.
It's still possible.
So that's it is possible to displace. So the corollary still holds true. So if you replace the lambda I had with these like concentric circles, then it's still going to be displaceable.
Interesting. Okay.
Yeah, so I don't know. yeah, so the question is open, I guess, whether you could replace it by something smaller, but it's not obvious what it could be.
Okay, okay, I see. Thanks.
Okay. If
Please,
there are more questions, just go ahead.
Yeah, I wanted to know how do you deduce that the Lagrangian is exact by this area estimate, please?
Right. Okay. Right. Yes. Right. So I want to. Right. Yes. Right. So yeah. So what I'd like maybe in this first case even.
Yeah, in the first case, yes.
Right. Okay. Well, okay. Right, so I'm using this lemma.
Mhm.
All right. So I have these Maslov two sections which have area S. Right. So I'm sure we're the best picture here. Right. So it's okay. So this is the case. Right. So it's actually maybe I'll go right. So right. So we're looking at Lagrangian torian here. So both of the tori bound a disk which bound a disk of area R which intersects one of the S axes once. All right. So if you like, you could kind of imagine gluing those two disks together so that neither of them intersect the S axes. So you have the two disks, they're both two disks of area R, one asymptotic to one Lagrangian, one asymptotic to the other Lagrangian. They both intersect the S axis. You could imagine kind of removing the intersection with the axis, gluing in a little cylinder, and then I'm going to get a cylinder between the two Lagrangians, which is going to have area 0. So that kind of half proves it. So that means I get one homology class. Right, so that's a way to produce one cylinder between the two Lagrangians of area 0. That makes sense? Right, so you just take the two like broken planes, somehow glue the broken planes asymptotic to one, the broken planes asymptotic to the other, glue them together. That's one cylinder between the two.
Okay.
Then we have to kind of repeat in the other class. So that's why this plane of area S comes in. So then we have to kind of play the same game with the T's. So then you look at those two. So those are Maslov two disks in the S2 times S2, but they're both intersecting the same axis exactly once. So I want to kind of remove that axis, plug in a cylinder, and then that's the cylinder. I don't know if it's but that's right. But somehow that's it. So I need the two lemmas that the broken planes have the same area plus the plus these Maslov two sections have the same area. And claim that implies it.
Okay, thank you.
That's kind of nothing too well. I mean, the difficult thing is this lemma here about the S. That's the key sort of calculation here.
Okay, let's see if there are any more questions, maybe. Maybe not. Maybe let's thank then Richard again for this very beautiful talk.
Thank you.